Nomine Patris et Filii Spiritus Sancti. Amen. Veni Sancti Spiritus, repletuorum corde fidelium et tui amoris in eis ignem accende. Imite Spiritum tuum me creabuntur, et radum vapis faciem terre. Oremus. Deus qui corde fidelium Sancti Spiritus illustratione docuvisti, da nobis in eodum Spiritu recta sapere et Deus semper consolatione gaudere per Christum Dominum nostrum. Ave Maria, gratia plena Dominus tecum, benedicta tu in mulieribus, et benedictus fructus ventris tui, Iesus. Santa Maria, Mater Dei, ora pro nobis peccatoribus, nunc et in hora mortis nostrae. Amen. Sede sapientiae, ora pro nobis. Sancte Alberte, ora pro nobis. In nomine Patris et Filii et Spiritus Sancti. Amen. Okay, welcome to your first lesson on stoichiometry. It's a funny sounding word, obviously, but it comes from the Greek stoichio, which is just a word that they used for elements, okay, are the smallest particles of matter. So, and as you know, meter or metry is a suffix that is going to mean measuring. So we're measuring elements, we're measuring the amount of elements or the amount of substances that we need to actually perform chemical reactions or to produce a certain amount of a chemical. And I like to call this is the chemistry cookbook, because this technique will allow you to basically take a chemical recipe, like for some particular chemical reaction, and calculate how much substance you need to actually make that reaction happen, okay, or make it perform. And so we get to talk about cooking a little bit because it's a similar idea. If I have a recipe for something, like this recipe I found for peanut butter cookies from bettycrocker.com, we have all of these quantities listed. A half a cup of sugar, a half a cup of brown sugar, a half a cup of peanut butter, but you'll notice that the units are not all the same. So I mean, some are cups. One whole egg is a completely different thing than a measurement in a cup or in a teaspoon. So we have all of these different these things have different masses, in fact, not only because they're in different units, but also because just they are different substances. So, peanut butter is maybe more dense than brown sugar, or maybe it's less dense than shortening. An egg does not have the same mass per volume as, a cup of eggs is not going to weigh the same amount as a cup of butter. It's not going to have the same mass. So these ratios are not telling us exactly how much matter is present in each of these items in the recipe, but they are telling us it's sort of more like a molar relationship that we have in chemistry. So I need this quantity of this in relation to this quantity of some other thing or of some other mass. And so if I want to know, how much it's, let's say I want to make more than just this one batch of cookies. Like, let's say this makes, actually you forgot to check this, but maybe this batch makes just 1 dozen cookies or something. So this batch makes 12 cookies, let's say. So if I combine all these ingredients in these quantities, I get 12 cookies as a result, okay, which is a new substance. It's like a new chemical from all of these other chemicals being added together and undergoing some kind of chemical reaction. If I want more cookies than that, because who just wants to make a dozen cookies, right? Let's say I want to make a triple batch of this. I want 36 cookies instead. I want 3 dozen. Well, then, as those of you who bake know, it's not too difficult to do this. You need to multiply all of these quantities by 3. So, I would need 1.5 cups of sugar. I need 3/4 of a cup of shortening. I would need 3 eggs instead of 1 egg, and so on and so forth. But the way that we might do that in more of a something that's close, a method that's closer to the chemistry is we can think of this as unit conversions, okay, which we've been doing all year and will continue to do. And stoichiometry is basically just a way of doing unit conversions, in fact. It's just like the conversions you did between moles and grams in chapter 7, but it's got just one extra little conversion or one extra step. So, let's say I want to make, let's pick a random number. Let's not do 36. Let's say I want to make 27 cookies. So if I want to end with 27 cookies, I want to know, okay, well, how much sugar am I going to need to make those 27 cookies? And we can set this up like a unit conversion, in fact. So if I have 27 cookies, the original ratio between cookies to sugar is 12 cookies comes from 1/2 of a cup of sugar. So basically that's this conversion factor. To make 12 cookies, I need a 1/2 cup of sugar. And so there's a ratio here between these numbers. Okay, or if I want to make 24 cookies, I need 1 whole cup of sugar, for example. And I can use this ratio between the different ingredients, or between the ingredients and the resulting substance that we make. I can use that as a conversion factor to figure out how much of each particular thing I'm going to need. So if I change my number of cookies from 12 to 27, how much sugar will I need? Well, I just perform this unit conversion. So I do 27 times 1/2, so 13.5 divided by 12. And that means I will need, my units now are cups of sugar. I would need 1.125 cups of sugar to make 27 cookies. Okay, let's say I want to make, or let's sort of flip it around. Let's say I used 4.6 eggs. Okay, don't ask me how to get 0.6 eggs. It doesn't matter, but we can still calculate that. If I use 4.6 eggs, how much, let's say, how much baking powder will I need to use? Or let's do baking soda. How much baking soda will I need to use if I am going to be using 4.6 eggs in my recipe? So if I increase the number of eggs by that many times, how much baking soda will I have to use in order for the recipe to still work? If I increase to 4.6 eggs, I used 1 egg originally in the original recipe for every 3/4 teaspoon of baking soda. And so again, I just use that ratio as a conversion factor. My eggs cancel, and now I will have 4.6 times 3/4 is 3.45. So I would need, if I'm making a certain amount of cookies that requires 4.6 eggs, I would need to increase the amount of baking soda I use to 3.45 teaspoons of baking soda. Okay, now this is, obviously this is a little silly because if you're cooking cookies, if you're baking cookies, you're not going to make weird batch sizes like this. You're just going to say, okay, I want to make 3 times as many or 4 times as many. And so the math is a little bit simpler. But the reason I'm using odd numbers here is in chemistry, it's not always going to be like that. You're not just going to, make 5 times as much of something. You're going to be maybe, increasing by strange multiples like this. So we're just getting practice so that when we go to the chemistry, we can see more easily how this will work. Okay, and if I had, let's say if I have 4.6 eggs, that means I need to use this much baking soda. Well, how much sugar would I need then in that case? And so I use that ratio between the number of eggs and the amount of sugar. So it's 1 egg to 1/2 cup of sugar. And 4.6 times 1/2 is going to have this, so I would need 2.3 cups of sugar if I'm using 4.6 eggs. And maybe, the ultimate question here is, well, okay, if I use 4.6 eggs, how many cookies am I going to end up making? Okay, again, remember, everything in the recipe has to change its quantity in order for this to work. So we're only calculating a couple of individual things, but all of these ratios would have to be increased by 4.6 times. And the number of cookies we're going to get is going to be increased by 4.6 times as well. So 4.6 eggs is equal to how many cookies as a result? Well, one egg gave me 12 cookies originally. So we're just going to multiply, basically we're just multiplying 12 cookies times 4.6, which gives us 55.2 cookies. So 55 cookies and then a little bit of batter left over for you to sort of eat and get salmonella poisoning from eating your raw cookie dough. Please don't do that. But I know that some people do. Okay, so this is basically stoichiometry, what we're doing here. The difference is that we're not actually reducing this to mass. So like in this many cups of sugar, this would weigh a certain amount. This would have a certain number of grams associated with this amount of sugar. There would be a certain number of grams of baking soda here. A certain number of grams of the cookies would weigh a certain number of grams or would have a certain mass. And in the chemical equations, that's what we're really going to be doing. Okay, we're going to be not only converting to moles, okay, or to a certain unit of the thing, but we're going to then take that and we're going to convert it to grams so that we know exactly how much mass of a certain substance we need in order to cook something up, in order to make a chemical reaction happen and produce the amount of chemical that we want. So here's an example. I have two chemical reactions here which are part of the same process. So this is the process for manufacturing or producing phosphoric acid. Okay, H3PO4 is phosphoric acid. You need to take elemental phosphorus, okay, in the form of P4, and you burn it, okay, or you oxidize it with oxygen and heat, and that combustion process produces diphosphorus pentoxide. And then you take the diphosphorus pentoxide and you add it to water, and that causes a reaction which will produce phosphoric acid. So this is a real life chemical manufacturing process that actually is used. So this is my recipe in a sense. Okay, it has two steps, or it's two separate recipes kind of, but it's one process as a whole. So just like in the recipe, we could have conversion factors between the various elements involved. We can do the same thing here using these coefficients. These coefficients, some of you have figured this out already from comments that I've heard you make, but these are molar ratios. In other words, if I have 2 moles of phosphorus and 10 moles of oxygen, I can produce 4 moles of diphosphorus pentoxide. If I have 1 mole of diphosphorus pentoxide and 3 moles of water, I produce 2 moles of phosphoric acid. Okay, so these molar ratios are the conversion factors that we're going to use in stoichiometry. And just like when we were doing moles to atoms or grams conversions, we always went through the mole as the bridge unit. It's the same thing here. You're always going to use in stoichiometry a molar ratio between these things. Whether you're just converting from moles to moles, or whether you're going from grams to moles, or grams of one substance to grams of another substance. You always need this molar ratio here in the center. So, some possible conversion factors that we could have for this process would be, maybe 10 moles of oxygen for every 4 moles of diphosphorus pentoxide. So I might use that conversion factor. 10 moles of oxygen is equivalent to 4 moles, or it produces 4 moles of diphosphorus pentoxide. Okay, so we can write that like that. Or we can use it the other way around, depending on what we're trying to convert to. 3 moles of water to 2 moles of phosphoric acid is another molar ratio here, or another conversion factor. Okay, so let's try using this idea to cook up some phosphoric acid. let's say I know that I have an order and I'm a manufacturer and somebody has ordered 1 kilogram of phosphoric acid. Okay, that's probably not how it would normally be ordered. It would be ordered as a certain molar concentration in solution or something. But let's just say theoretically we need to produce 1,000 grams, 1 kilogram of phosphoric acid. So if I want to produce that, the question is going to be, well, okay, well, how much of my ingredients do I need to produce this batch? This is like our cookies. If I want to produce this many cookies, please don't eat these cookies. This would be a very traumatic experience. Phosphoric acid cookies, I can't recommend them. If you want to make this size of a batch, how much do I need in terms of the other ingredients that make up that batch? That's really what we're doing here. So let's say first I want to know how much water I'm going to need to produce this batch. Well, I need to know, since these are molar ratios, I need to know how many moles of phosphoric acid this is first. I need to turn this into moles, and then I can convert between moles of water and moles of phosphoric acid, and then I can convert the moles of water to mass of water, okay, or the number of grams of water that I will need to produce this much phosphoric acid. So we need to know the molar mass of phosphoric acid, okay, and you already know how to calculate this. You just add up the molar masses of the individual elements, and it turns out in this case that 1 mole of phosphoric acid is equivalent to 97.995 grams of phosphoric acid. Okay, and now you're starting to see also why I insisted on you including the chemical names as part of your units in these unit conversions, because we're actually going to be changing chemicals here. We're going to be going from units of phosphoric acid, grams and moles, to units of water, okay, or some other chemical. And so it's actually important to do that to help keep track of what is what in the conversion process. So now I'm in moles of phosphoric acid. I want to know how many moles of water that's going to be equivalent to. Well, I have 3 moles of water for every 2 moles of phosphoric acid. Okay, so now I've converted to moles of water. And then how much water is that in terms of mass? Well, now we use the molar mass of water and we perform that conversion. So in 1 mole of water, there are 18.02 grams of water. Okay. And now we know, okay, this is the stage where we have the units that we want. This will tell us how much of this ingredient we need to produce this much product, this much of the phosphoric acid. Okay, when I perform this multiplication, I've already done this in advance, but you would just punch this all in on your calculator, multiply this, times this, times this, times this, divide by that, divide by that. It ends up being 275.77 grams. Okay, so with 275.77 grams of water, I can make 1,000 grams of phosphoric acid if I have the other ingredient in the right amount. Okay, so how much of the other ingredient will I need to make that 1,000 grams? Well, it's the same idea, it's the same process. I start with my batch size, okay, or my amount of my product. But instead of using the ratio between water and phosphoric acid, I'm going to use the ratio between diphosphorus pentoxide and phosphoric acid. But the first step here of going to moles is the same. I still need this conversion factor between moles of phosphoric acid and grams. Okay, but this ratio now is going to be between diphosphorus pentoxide and phosphoric acid, okay, which is 1 to 2, or 1 mole of P2O5 produces 2 moles of H3PO4. And then I need the molar mass of this in order to calculate the amount in grams of diphosphorus pentoxide. Okay, and that is 1 mole of P2O5 is equivalent to 141.94 grams of P2O5. Okay, and so again, we're set. We got to the amount of this ingredient that we needed. This comes out to be 724.22 grams of P2O5. Okay, so if I want to produce 1,000 grams of this, I need 276 almost grams of water and 724.22 grams of diphosphorus pentoxide. That's my recipe. Okay, for this size of a batch, that's how much I need in terms of the ingredients. Okay, we can work the other way as well. We could start with this much water and then find out, okay, well, how much phosphoric acid is that going to produce? And you basically work the conversion in the other direction. Let's take this now, since we know how much diphosphorus pentoxide we need. Let's take that and now figure out, well, how much phosphorus do we need to start with in order to produce that amount of diphosphorus pentoxide? So now we're sort of taking this amount and we're saying, well, okay, if we end up with that amount of diphosphorus pentoxide, how much phosphorus did we need to begin this whole process? Okay, because this is the first step. So now I'm saying if I want to produce 724.22 grams of diphosphorus pentoxide, how much phosphorus do I need? Okay, well, I need to convert this to moles so that I can go to the moles of the other substance and then to grams. So I need to use this conversion factor again. 141.94 grams of diphosphorus pentoxide is 1 mole of diphosphorus pentoxide. And then I'm going to use the molar ratio between these two substances that I'm interested in. There are 4 of these, 4 moles of this for every 2 moles of phosphorus. So 4 moles P2O5 for 2 moles of P4. So now I'm in moles of phosphorus, but I want to know grams of phosphorus. So again, I need the molar mass of this. And the molar mass of phosphorus 4 is 123.88 grams. Is 1 mole. Oops, excuse me. Got this upside down. Okay, so flip these. And we'll be left with grams of phosphorus. And when I perform this calculation, I will end up with 316.04 grams. Oops. Okay, so that's how much of this ingredient, the starting ingredient, I need that much of that to produce this much P2O5, and I need that much P2O5 and this much water to produce 1,000 grams of phosphoric acid. Okay, so you can work these in that direction, or you can work them in the other direction, but stoichiometry is powerful for knowing exactly and finding out exactly how much we need of some substance in order to create a desired quantity, okay? Because you don't want to sort of just be playing around with something like phosphoric acid and hoping that you're producing the right amount. That can be very dangerous. So in order to, perform the reaction safely, you need to know what quantities to work with. If you're producing something explosive, for example, also, you don't want to accidentally make too much of it or just sort of throw a bunch of stuff together and hope that you get about the right amount. Like, trial and error is not always a great way to go when it comes to chemistry because of the dangers involved. So this gives us a way to predict the amounts that we need in order to form the amount that we want and keep it sort of under control. Tomorrow we'll have another video looking at some more examples of this and explaining a few other small points, but really that's the essence of it. It's just a different kind of unit conversion. So it shouldn't be too difficult if you already have down and grasp the unit conversions that we did in chapter 7.